get ready.
Okay.
So, do you remember what we talked about and what asked you to actually work on?
Yeah. So you told me to look at all the different cards in the specific areas. So like what I did was I kind of just looked at them and like here, I'll show you. Okay, so
So, one thing I wanted to ask, did we run an example using from player?
um we were going to do that, but we had an error. Like
Uh,
I think the error was that I looked at it after the meeting and it said G77 was not found. So I might just have to like download that.
no,
Um,
actually, we can we try once?
okay.
I think
Yeah. So I just go to run.
yeah, you
Um,
can try one cycle.
okay. So I just click start.
That's there are 5 cycles at this point. Let's run one cycle.
Oh, it did it. Okay. Oh, I mean, it seems like it's doing something. I think I had an error when I tried building. That's the problem. Like when we tried building our own input file, I think.
Oh, okay. That's actually interesting. So let's go through this in a run. So once you do the compilation, that's how you run the simulation.
Yeah. Once you like finish putting all the inputs and stuff and like
And then
making all the
compile. Yeah. Let's go to viewer. You see the viewer. You see the calculator at the right, top right.
let me move. Sorry, the zoom thing is in the way.
You see the
Yeah.
calculator there? Yeah. Let's go to the viewer. On where is the other card went? Only we have two of these. No viewer there.
There's oh right here.
Yeah. Can we go? Oh, okay. So load. Let's look at the dot out file.
Okay. This one.
No, another. Yeah. Open. Let's go to the run summary. You need to play around things and learn, need to become familiar with this.
Okay.
Let's go to error. Yeah, I think it says error, but that's what the run summary is, something like that. Let's see. So if you see this through viewer, right?
Yeah.
You see again if you look at this file, it's just a text file, a lot of stuff. But when you see the viewer, you can look at different parts. Can you go to an input echo? So this is basically how your input is interpreted. So
Mm,
what you write there and what it is interpreted, it may be a little different. It basically a chronological order in which your program is looking and setting things and moving on. So this is good because if there is an error, then you know where the error is. But this is of less of interest for us now. Let's go to material. So you see in the same output file, we do not use all these materials, but can we go to regions? You see, those are the region: vacuum, black
yeah.
hole, vacuum, beryllium, right?
Hmm.
Events by region. So any simulation you do, you need to do the sample simulation so you understand, what's going on. So can you go
Okay.
to events by region?
Is it around here?
Yeah, events by region.
Oh, right here. I didn't see the full thing.
So there's a lot of information. You need to actually learn a little about it. But in a, I think it should be fine for now.
Okay. I took the time and I like kind of learned what stars were, and they're like stars are just interactions, right? Hadron interactions.
Yeah, stars are when there is an inelastic interaction where a particle is produced, then you say that one star is formed. That's what I think. So if neutron comes in and knocks out proton, then that's You counted that as 1 star. Yeah, but I think that's less relevant. We are still not there yet. So can we go to geometry tab at the top now? Let's just play around with this.
Okay.
So did you try, working around? Can you zoom in?
Yeah, I tried zooming it out. And this is
So you
this is
see?
what the region looks like.
Yeah, so you go to, that box at the top. You see
Uh,
the region
mm,
on the left.
oh, yeah, right here.
Yeah, go to regions. Now, if you click on that type and name, it highlights. Type on region, one region. You see? So this all is some region that it's defined as black hole, region BS1. Type,
Um,
click another region. So that's the, volume in, inside that black hole. That's likely vacuum. Another one. So you see it's highlighting, right? So it seems like the region is very small. Can you zoom in or zoom out? I don't know how to zoom out.
maybe
Yeah,
you
you
zoom
see?
in.
Yeah, so can you see beam part? Can you press beam part?
Right here.
Yeah, it shows even the direction. Do you see something?
I see
Arrow.
the point. Yeah, that's the position of the beam center.
Look at the, second one on the left. I suggest, we you do not, touch this in a screen because it's also possible to change things there.
Okay.
So you see the arrow?
Yeah, right here.
Yeah, that arrow shows the direction. So if you look at the z-axis,
Mhm.
if you
Is
move it a little up, if you move this screen a little up,
how do I don't know how to.
just
Oh,
go. Okay, just use your cursor and move that up. You can do that.
um,
So you can see now at the bottom. Oh, okay, actually it's the zoom problem that I cannot see your bottom there. So can you, yeah, you see what's the direction? What's the
this
direction
is
of the particle?
um positive z because the arrow is pointing this way and the z-axis is this way, so it's in the
Yeah.
positive z direction.
So for monoenergetic beam, the thing that you need, that defines a beam is a particle, momentum or energy, and direction, right? And
Yeah.
position.
Okay.
Let me, so you need to play around with this actually.
Okay.
So one thing, I just want to touch on this. So the run was successful.
Mhm.
The default executable during the compilation, in this case, rfluka is being used.
Okay.
So let's try to compile again if there is a problem.
Okay.
So if you go to run again, run, let's go. I'll teach you one thing. Run. You see they're clean.
Yeah.
If you clean that, the run, all the files that were generated in this run is removed. Can you press that? Yes, that's how it is removed. If you go to compilation, compile,
Right here.
yeah. Let's remove this compilation as well. Do clean. So even the compile in a file that you get, right, something like exe that you define, it gets removed. So
Oh, okay.
in this case, you did a run where lfluka was the default executable that was used.
Mhm.
Let's try ldpmqmd and build. Just name it anything. I think it will. Okay, good.
Yeah, this was the error that we got last time.
Can you see that?
Yeah, I think uh right here, G77 not found. Does that just mean because when I open the terminal,
Yeah, I know what's happening actually.
Okay, because it doesn't say that there's G77 for this
Okay,
computer.
so let me see. Actually, there is no G77, but it is asking for a G77 instead of Fortran. So let's go to Flare screen. Okay, maybe it's good for me to actually, open my Fluka here as well, so I can actually guide you. Okay. Yeah, I think you need to actually, play around this. I think you are not yet ready to make one big step, because now next we'll be making a big step.
So you just want me to just play around, just do a bunch of random stuff with it?
Yes.
Okay.
You have to make sure that you do know how to compile a running example, learn about the input cars, and one more thing that I'll talk about. But let me see where you set the executable.
Okay.
I forgot actually what used. So let's go to that auto file. So you see, it is looking for G77. Instead, we wanted it to do that with G Fortran.
Okay.
So let's see how the let's from the terminal echo flupro and flufor once. Can you write what's the G Fortran version?
Oh wait, sorry. Uh, 11.4.
Yeah, somehow we need to link that to actually look at G Fortran. I forgot actually. I may have had that problem in the past, but I need to remember.
Oh.
It seems like when there is no G Fortran available, it's asking for G77. That may be something that has been written in that RFluka. That compilation is script.
Oh. Mm.
So but we know that we have installed G Fortran. We ran Fluka, so it need to identify. It need to pick G Fortran when we compile things.
Yeah, so there's a variable that's not pointing to the right directory.
Yeah. So can we see the output when you run that?
On the terminal.
Yeah, let's repeat that run. That
Okay.
we can we
Yeah.
go back to Flare?
Oh yeah, right here.
Yeah, so let's go to compile again. Let's use the default one, Fluka.
I just click build.
Yeah. Yeah, you see. So when you do run, your run was successful because you don't need to compile because Alpha is a default executable.
Hmm.
But when you want to create LDPM QMD, you have to create your own executable and it should understand Fortran, G Fortran. At this point, it is looking for G77 that we do not have. And
Yeah.
G77 is too old. So we need actually in a G Fortran.
Okay.
So let me think about this, why. Oh, okay, now I see. Can you click clear at the top? No, no, flare in the, yeah.
This one?
Come back, come back. So that's the flare you see, like flare, yeah, that one. And then you see config.
Right here?
Sorry. Wait. So you see the compiler? Click that compiler. Choose.
Oh, okay, okay. I see, I
Okay.
see.
Okay.
Yeah,
Because this is a flare at the top hierarchy, right? Flare is the
yeah,
project. So let's try compilation again.
okay.
Note that down in that PowerPoint, okay? Because I think this problem people may often find.
Okay, I'll do it after.
Yeah. Can you build? I hope it now it's successful.
Yeah.
You see, can we go into that screen, little screen at the bottom, just to see?
It didn't let me click on it.
Yeah, that one. So you see there now, if you go to the top, now it's using Z Fortran, you see, and not looking
Yeah,
for
yeah,
Z7.
okay. I see.
So
I just
that
needed
worked.
this.
Now let's go to run and then clean the earlier result. Let's start. So that part is fixed now. I'm actually happy about it.
Should I press again? I don't think it did anything.
Now it's waiting to attach.
Oh, okay, there we go. It was just lagging.
So we solved one problem. I'll talk about one thing in 5 minutes and then you can, we can meet next week. So let's go to the viewer and output.
Oh yeah, okay.
So now you have to load again because this is something out of the memory from earlier output. Uh, okay, viewer, load. Which one is the output? Recent output.
Probably I should have made a new
Yeah.
terminal.
Or if you clean it, usually that goes away. But maybe let's try exdfi.1.out and maybe that one. Let's get in. Let's go to the run summary again. Error. I don't know why things appear. What should appear in? Oh, okay. That's the way you can access. Okay, it's actually
Oh.
better. Yeah. So
I just didn't know to double click on it.
yeah, it seems like your flare is GUI is much more advanced than mine. Let me see if that works for me. Yeah, actually, I had never. Yeah, I like that run summary always because there's a lot of things, but still you see the energy balance there.
It lists all the particles even if we don't use it.
No, that's
But
something you should not assume. It depends on what particle. So if the collision is energetic, you can produce secondary particles. We haven't even looked at what's the incident particle is, right?
Yeah.
So if
Okay.
you want to
So
understand this, you can say whatever particle that is, it produced like 10% of whatever secondary particles after collision it produced. You could say that 10% is like alpha, 0.7% like 3 helium. So it must be energetic collision in this case. Even pi zero, maybe something like pi is the pi zero is the maybe pion is the incident particle. We do not know. We'll look into that. But let's go to the energy balance. So there's a lot of things. Yeah, you see, most of the energy was gone in G, hadron, and muon. So let me tell you one thing. So any one good simulation, perfect simulation, that you can trust the results to, you have to look into great details. And it's often good to read this output file, particularly run summary, events by reason.
oh,
I usually like material reasons, events by reasons, run summary. So there are a lot of things. I think one task you'll do is you'll go to the fluka.org site and then find somewhere manual where it talks about what's the default output, because this is the default output of Fluka. We may ask for some other output. We may ask for energy deposition. We may ask for flux, right?
yeah.
So what I mean is just task one I'd say is learn about what's the default output.
Okay.
So you'll have to keep in mind that there are two dot out files. One dot out file just tells about the job, the simulation, while other tells about simulations and processes like this. So I'm
Okay.
talking about this file.
I see.
So task one, I'd say you learn about what these mean from some manual, because that's something it's earlier you do, that's better.
Okay. Task two, play with fluke flare. Play with fluke and flare.
You don't need to. So you can look at this flare, whatever you see here in the left at this point.
Mhm.
But I suggest you go to the manual and just learn about the default output, because it helps you to debug things later on.
Okay. I'll try to find something later then.
Yeah, you can even go through this actually. So you'll try to find it yourself. Just something that summarizes what Fluka writes in this dot out file, because this looks all identical for any simulation. And this is something you get by default. You may not use that output for some analysis, but it will be important later on for two reasons. One, to make sure that you are doing things correctly. Next, to debug things and compare, because I like run summary as well, because it helps you to compare.
What would you actually use for analysis?
For analysis, we define our own output the way sample
Uh,
output used
by
to.
using McDraw.
Yeah, so yeah, we'll do that in sometime in the future. But before that, what I wanted to tell you is Fluka can provide you output itself.
Okay.
There is a lot of default scoring. You don't need to do anything. Just use appropriate cards. If you want energy position, just use appropriate. If you want flux, but if you want information event by event, that's actually a very important point. If you want information event by event, we'll have to work with McDraw. And that's what happens when we are interested in backgrounds, because there will be only a handful of events. But if you are interested in statistically average quantities, like average energy deposition, what's the spectrum of the energy deposition? What's the distribution of neutron number in a given region? These things you can just average and look at the spectrum. But if you want the information in event by event basis, we'll have to use McDraw, and that's something we have to do at some point in the future.
Okay.
So I think we'll start working with DarkSide 20K file in a couple of weeks time. Not next week, but maybe following week. And then you
So
try. you'll start understanding things. Because you know that Tina ran DarkSide 20 files. So I worked on that heavily in the past. She has source file, she has Megra file. So at some point, we have to ask how to provide the files, compile, and run in the flare with just say 100 events to ensure that it runs successfully. So that would be the first part.
Okay, so the goal is to run the dark side files, but first you want me to get used to the the compilation and the outputs.
Yeah, I want you to understand this before we actually look at the real memory. But the thing is that for DarkSide 20K, maybe we'll first test is whether it runs at all, right? You have to compile, right?
Yeah.
So let's try one thing, and I want you to remember that because it should not be much different when you play with in a DarkSide file. Let's go back to compile again.
Okay.
So if you remember, when we actually ran that through Fluka, we actually linked a source.f for an example. Do you remember?
Yeah, the source file.
Yeah, so let's try something like that. You see the add button there? We do not have DarkSide 20K file, but let's take one or both because
Can
these
I?
are Fluka's file, right? Yeah,
Yeah.
let's link them. So we linked them, open, and then let's
Uh.
compile. Let's compile.
Okay.
Now, if you go to that little screen at the bottom, it's a little different than what you did earlier. You see at the top, it is linking those files as well and creating an executable
That's exactly what we did on the
with
terminal.
Fluka. Yeah. So with DarkSide, this is what is going to happen. You'll have some source file, some Megra file. So this is a sample we tested, but this would be the first thing. And this is something you can even try yourself. Once Tina provides the input file, source file, and Megra file, just trying compilation and running with 100 events. So we need actually a standard file that Tina worked on and make sure that we know that copy. So when we start changing, in case we need to do, that we do not lose that original copy. So original copy of input file source.f or megra.f should exist in some way that we make a copy of it and we'll start playing around and changing things.
Okay, that sounds very good.
Now, one
This
other thing I wanted to say is this is already a good progress, but this cannot be faster than what we are already doing because you have to learn on the way to actually jump into simulation. So what I ask you to do is you can play around one thing. If we go to the input, so I'd say task one would be to learn about these cars, right?
I did. I
And
learned about them.
then yeah, and then task two is learn how to change things. So for example, right now let's do one thing. Let's go to the top and likely we'll work with me once. Let's write instead of proton something else.
Okay.
Just remove. Wait. Can you click right? Click and add primary beam. Oh, okay,
Oh,
sorry.
uh,
Yeah, maybe that looks a little different than what I have in my flare. So I
yeah.
suggest you just go to where the proton is written.
Oh wait. Let me
If you
delete this.
yes, go to proton. Yeah, actually, there should be something easier than this. Yeah, that's the way you define. Yes, I think this part is a little different because my flare doesn't have define, so you need to learn how to define. So press that in a box where you wrote me one, and then go to that help section at the very top. You remember that help?
This one?
Yeah. Uh, I think
The
no, we didn't press at a proper place. Let's remove this. Can we go back again? Yeah. Oh, okay.
I think it's only the define area that does that, but if I do it on this, oh, if I do it right here, it'll tell me about it, like what each
Yes.
input
So
is.
you have to learn, play around with this. Just change, me one, buy into something else. But every time you make a change, make a copy of it. You see their save button. When you change in the input, there's a save button. You define something else, xdfi one or two or whatever you want.
Okay, that sounds
And
good.
say, and similarly, you can also save Flare, the entire project. So it even removes the compilation. You go to the Flare, and then they just save.
So all of the compile
Yeah,
files,
everything.
all okay, okay.
Yeah, and then you can just name it and save it. Can you click that once? Yes, you define it, and that goes. So just please around this.
Okay.
So the
Yeah.
last, yeah, you learn to change things. Geometry, do not worry about that right now. Geometry is a complicated thing. So next week, I'll provide one simple task for you where you'll just fire me one into say aluminum, a simple problem,
Okay.
and
You want me to
record
do
and
oh,
record just say energy. So we'll talk about that next week, but that would be a simplest problem.
you want me to do that by next week or we're doing that
Uh,
next week?
Next time we'll meet and I'll show you how to do that.
Okay.
And then we'll learn a little bit about how to change geometry as well next time. Now let's go back to the top general. General is very important actually. Title. I'm still confused. Can you go to primary? There should be one card at the very top. Do you see the card defaults somewhere there?
Default.
Card named defaults. DEFAULTS.
Defaults.
In general. It should be in general.
No, I don't see one called that. Maybe we should add it. I don't know.
So let's wait, wait,
Right here?
wait, wait,
We can
wait,
add this.
wait, wait.
Okay.
Because, you need to find a proper place. Let's get out of this. Let's click on title
Yeah.
card. Title card. Title card.
Yeah.
Click right. Right click there. Add. No, we didn't do that properly. Again, let's go back and add again. Yeah, right click. Where did the add go?
The add right here.
Yeah, you're not, don't, click on that title name. Click, somewhere, outside that, right click. No,
Okay.
not outside. Click on the title card
Yeah.
and then go there. So this is a big box, you see. Click somewhere
Yeah.
there. No, not on the language. Just
Somewhere.
somewhere else in that card.
Somewhere here.
Yeah. Yeah, somewhere outside. Yeah. This is a bigger. Click right. Why can't we see add? So let's go to general. I don't know what happened.
Here.
Wait, wait. Oh, okay. So can you go to defaults? Yeah. So you see, we just define a card named defaults. Look at the arguments. There are a lot. Calorie,
Damage.
damage. EM cascade, ET trend, hadron therapy, Icarus, neutrons, new default, precision, shielding. So I wanted to actually talk about this a couple of minutes, just leave it as it is. So what happens is, it is not an easy thing to actually define the car and write all the cards that are relevant to call all the physics processes that you want for your simulation, right?
Yeah.
You understand what I mean? For
Yeah.
example, yeah, if a in an energetic muon passes through aluminum, it could actually produce ionization. So you need electromagnetic physics. It could potentially produce, say, secondary particles like gamma, neutron, and such, right? So that may involve Newton physics, hadron physics. So, depending on the problem of interest, this card allows you to load all the physics processes relevant for the simulations of interest.
Is that similar to when we were making an executable?
Yeah, executable is a little simpler because executable is because we wanted nucleus interactions. So we created LDPM. That was all. We activated nuclear interactions in our simulations in a sense. Okay, but this is a little different.
Okay.
This is basically a kind of in a you could say Fluka is making users making it easier for users to do this. So I want you to learn through this. You see calorimeter. So what kind of physics are on when you use calorimetry as your default? You see there all the
Yeah, I
description.
see. Yeah, I see that. Wow.
Yeah, let's go down all the way to precision. So you learn that because it's good to know the physics that you activate. Precision is the most precise one, I would say.
Okay.
Precision means it activates almost all. But if someone is not interested in this level of precision or certain physics processes that's written in here, why someone would waste the compute and resources by turning this card on? So that's the rationale behind having so many cards.
Could you add multiple defaults?
No,
It's just
we
one
add
default?
we add one depending on the problem of our interest. You got the
Okay.
idea of why these cards are there? If someone is interested in just electromagnetic physics, just working with 2 MeV photon that would never produce neutron in most of the materials, why would they be interested in newtons, right?
Yeah.
Why would they be interested in defaults? Because when you actually want more precision, you are activating more processes, and computationally it takes quite a long time. You understand what I mean?
Yeah.
So basically, based on the problem of interest, people usually start from one set of physics, and that's what is defined in defaults.
I see. Okay. So
So
you
in
just want me
our
to
case, so you'll have to go through this. And particularly, I'd say you just go through that, read through that once, and learn about precision. Start.
okay.
So what happens is, in our case, we'll use precision.
For dark
Because
side?
yeah, because when you fire cosmic ray muons that are so energetic at the depth of Grand Sasso, where dark side lives, you are going to have a lot of processes. You'll produce neutrons, you'll produce photons, electrons, gammas, and those particles will again interact, and you'll have to have basically full propagation of all particles, then allowing them to propagate, interact, and then again transport that particle. That's what the simulation does. You understand what I mean? If a muon comes in and knocks a neutron out, then that neutron also has to be tracked out alongside the original muons. That neutron will say knock another 2 neutrons out, and they all will go in different directions, knock protons out, produce gammas, and then will be protons in ionization and a lot of things. So each of these things should be tracked for that one event I ran. So
Okay.
precision actually encompasses basically bulk of the physics. We want that. We want to include. So you can say that in our event, there's a lot of physics processes happening. And a lot of those physics processes are called when we use this as default. You got the idea?
Yeah.
So another thing I wanted to say is, so precision, let's say precision as a default. and then I'll say even more interesting things. So can you save? So this is something I want you to remember, because once you turn defaults and then start running simulations, you know, we may do it wrong.
Oh, I'll just go in here and say as a habit.
So this is something I also wanted you to keep in mind actually. You understand what I mean? Any
So,
simulations, any analysis you'll do, you'll use precision. Now the interesting part is, even precision does not cover all the kinds of physics that we need, because muons are in a hundreds of GeVs. Mean muon energy at Grand Sasso is something like 270 GeV. So you need to call hadronic models, the models that is even not covered by precision card. To add new physics that precision does not cover, we need to add things separately in what is called physics card there. You see the physics card?
right here.
Yeah, let's click that. Physics. Can
There's
we see?
nothing in there.
There's nothing in there? Okay,
Yeah.
it's a very simple cases where even default would work, whatever default. So, maybe, you can try another example, just if you want to learn a little different, but not now. You understand what I mean? So we have to define additional physics cards if we want to simulate things properly and do any analysis in our output ultimately. So this is something I want to tell you very early on, because sometimes people just forget. They use defaults and then they have not activated inner processes, and you could easily underestimate the backgrounds. Because for us, background is very important, right? For dark side quantity,
Yeah.
Newton background. So that's all I have. I think you could play around things, learn little bit about output, learn about you know default precision card, run some other example and look at how different things are in terms of physics and transport. I'll not talk about transport at this point, because we'll talk about that later on. So this is something we can talk about later on.
I know
But just
transport.
yeah, so just get familiar with this. Your simple example, in one way or the other, your simple example where a Mi1 of say 100 GeV hits the aluminum seal of say 2 meters. What's the energy position within the aluminum seal? What's the flux that goes out? So we'll start from one simple problem. Unless you solve that problem and get see something, I think you are not yet ready to actually get into dark side simulations, because that will also help you career wise, because you'll have done something on your own. You can use Fluka for some other purpose other than dark side. So that's the natural course I take. You understand what I mean?
Yeah,
So
and I could
maybe,
teach it to other people.
yeah, maybe in I think 3 weeks. So this next time we will meet, first meeting, second meeting, and third meeting. I think in third meeting we'll start playing around, dark side 20K files. Maybe third, not maybe fourth, because I think it's good for you to solve one problem, simple problem.
Okay, so my current task is to play around with compiling and Luca and learning about the precision card
Yeah.
right here.
And if you want to run more, learn one more thing, because when you make a simple example, we need to record something, right? We need to score something. We need some output. So, I would ask you to learn user bean and user track for now.
Okay, this one and this one.
Yes. So you can learn, because you can record a lot of things using those two cards alone. Actually, in my entire Fluka career, the default Fluka card that I have used is just two and another one. So you can do a plenty of things. So the end goal is in not only working and doing simulation for DarkSide 20K, but you also know Fluka, that you can use it on various purposes later in your career. And that's basically starts from scoring some output. So score that output, we'll use user bean and user track. What you can record What you can do, just learn that. If you learn that, I think that should be good enough.
Okay.
So I think so this is something I generally, so this is something that's my opinion. So I suggest you talk with you know Dr. Son about what I suggested, because if he wants you to get involved with dark side quickly, then we can make an alternative path. But I think if he has no other suggestion, and I'd actually go along this path. You learning things, doing one simple thing. You define, maybe even we don't need to define aluminum. I'll show you how to define aluminum. Later we could define rock.
You just
Actually,
define it.
yeah, actually I'll find you a very beautiful problem.
Would you just do it here? Like
Yeah,
in the
need to worry
assignment
about
room?
that. Defining material, I'll teach you a very simple case, and then you'll start working on that. So I think if I were to do this, I'll assign you one simple task to learn about all these cards and how to set things, and then another one task where you actually simulate in a way similar to what you do for that side, but in a very simple setup. So we'll have two tasks, I would say. One task is just learning things, running things. We could use this example input. That should be fine, right? Second task, where can you write down the second task? So we can think about that in say 2 or 3 weeks time. You learn what's the mean muon energy at Grand Sasso is, and fire that muon of that energy in Grand Sasso rock of 5 meters, where you fire muons vertically.
Fire the muons at Grand Sasso, like the rock.
Yeah, we'll
The rock.
we'll model the rock, Grand Sasso rock, and then fire muon of 270 GeV muon passing through the rock, and then recording how many muons survive. And recording what is the Newton spectrum like from that muons coming from the other side of the rock. I think that would be a beautiful problem.
You want me to do that by next week?
No, so
No.
that's I wanted
That's
you
just
to
a future task.
find
Okay,
it.
just think
So
about it. Okay.
yeah, so so that's something we'll do one mock task in 3 weeks time, and I'll have to actually guide you. I'll guide you through this a lot of these things. But this is more of something you could say a little bit complicated task where you learn to do things independent of me. That task, and we'll see something interesting that we can easily compare. So I like that example actually.
Okay, that sounds good.
You like the idea, so you can actually talk with Son as well what he thinks about it. But I think it's good you know Floka well, so you prepare yourself for any kind of simulation in Floka in the future, and at the same time you learn just enough that you transfer that to someone else in future. So that's
I have all these videos recorded, so I could just go back and learn them. And then I could like make it a course.
yeah.
So because we're already going through everything one by one. So
Yeah,
I could also show people these videos.
yeah, yeah. I think that should be it.
Okay.
I don't want to overwhelm you, but I want you to learn and play with things. You don't wait for me to tell you what to do. You can, if you want
Okay.
it, you can play with region, material, how people do it. You can learn everything.
Okay,
So
I'm
let's
just
do
gonna
one.
do random.
Let's not meet next week. I want you to be I want you to actually learn few things independently. So let's meet in 2 weeks time.
Okay.
It gives you room to actually explore things on your own without me actually guiding you. At the end, we have to define some material, we have to define geometry, we have to define our physics processes, we have to define what we want to score or what we want as an output, right? That's what the simulation is. And then we compile things and run the simulations. So that's basically in a summary of what we have to do. So this all these things, you can actually learn from a simple example like this. Maybe you can even learn some tutorial where this example is explained. It may possible. It may be
This is
there.
unrelated question, but for the internship, are you allowed to be one of my recommenders?
For which internship?
PNNL,
No,
the
I can't be recommended
okay.
because most likely if you apply, they may find me match me, and so I can't be recommended in that case.
Okay. No, yeah, that would be cheating. Yeah.
Yeah. Okay, so that's all, Matt. Keep working. So see you in 2 weeks' time. I'll
Okay.
cancel the meeting for next week. Okay.
Okay. Thank you so much.
Okay. Thanks, Matt. Take care. Happy Thanksgiving.
Happy Thanksgiving.
Bye bye.